Hello, good morning. Can you all hear me?
Yes, sir. Good morning.
Right. How about the board? Is it clear?
Yes, sir.
Whiteboard? Yeah. Right. Shall we start? Still? Yeah. Okay. Now only people have coming in. Um, all right. So, shall we start then? Hello. Shall we start? Where are the batch rep and repi as well as rep? Are you all around?
Yes, sir.
Right. Shall we start then? Your quarter was. Did you had any lectures in the morning?
Sir.
Huh? Yeah.
Yes.
Till what time? Till what time?
8 to 9 agronomy and 9 to 10 biology.
Okay, all right. Okay, so you had enough break, right? Hope you had at least 15 minutes break. Fine. Shall we start then? Today I'm not going to use PowerPoint. I'm going to use basically manually writing on the board, which is more effective, I assume. Right. Just to refresh what we have done last time, if you have given a distribution of a particular random variable, right? We said if a random variable is normally distributed with the mean of mu and with the variance of sigma square, then we can convert this into z distribution, which is also normally distributed with a mean of 1 and with the variance of 0. So in the z distribution, the mean is always 1 and with the variance 0. Sorry, the mean is always 0, the variance is 1. Mean is 0 and the variance is 1. So if you look at this normal distribution, mean is mu and it has a variance. So you can take standard deviation, doesn't matter. So here, if you have again a normal distribution, this is called a standard normal distribution. The mean is 0 and the variance sigma square is 1. Whether it is sigma square or sigma is 1. If it is 1, square root of 1 is 1. So we originally, any random variable will be distributed like this. Then since we are unable to find out the probability, if we want to find out the probability, right? Probability of, let's say, x between this is x, this is y, right? A and B, right? Probability in between A and B of the variable x can be converted this into the z, where we can call it as probability of A minus mu divided by sigma, and it will be converted into z, B minus mu divided by sigma. So this will be converted into z form. So this is what we have done last time, and we have used the formula z is equal x minus mu divided by c. So this is the formula that we have used. Okay, to convert a normal distribution to the standard normal distribution. So this is what we call as Z-score. Maybe in your A level, you have heard about Z-score. So everybody has a Z-score. Normally, what they have done in the calculation of Z-score for your subject, if you have done physics, right? If you have done physics, for example, let's say x1 is a physics normally distributed with a mean of mu 1 and sigma 1 square, right? How did they calculate the physics Z-score for you all? For example, Z is equal your physics score, your own physics score. Let's say your physics score is 60, let's assume. Then the average of all the students who have done the physics, or in other term, mean of all the students who have done physics. So let's say that is mu1 divided by the standard deviation of all the students who have done the physics. So you know how to calculate the standard deviation. You calculate the variance and so this is one. This is what we call as how we calculate the Z-score for each subject that you have already done for A level, right? That you have done already for A level Z-score. So what you want to know? You want to know three things. First, your own score of physics, your own marks of physics subject. Suppose let's say that you know 60. What are the other two things that you should know to calculate the Z-score? Overall mean. That means mean of the everybody who has done the physics. So that we cannot have it as a personal, isn't it? That only UGC knows. And also this mean as well as standard deviation that we don't know. If you have mean and the standard deviation, then we can find out our own Z-score. Only the higher rank officials in UGC, they know the value of this and this for each subject. That is how the Z-score has been calculated. So what they did is they calculate the Z-score for physics separately, chemistry separately, biology separately. Then they take the average. That is the Z-score which is coming to you in your final sheet. After A level, in your final sheet, you get the average Z-score from all three subjects. I showed you for physics, for chemistry, and for biology. If you have done agriculture, of course, agriculture, biology, and the chemistry. Right? So this is how Z-score has been calculated. Hereafter, you can go and tell your brothers, sisters, younger brothers, younger sisters, how the Z-score has been calculated. Right? Even at the UGC level, this is what they are doing. So everybody should know now what is Z-score, but you cannot calculate your own Z-score. Why? First, you should know what is your marks. Your marks, average marks of the whole group, whole population, then they are standard deviation. If you know all this information only, you can calculate the Z-score. Is it clear? There may be further, if you want to just maybe in 2012 there was some crisis of new syllabus and all syllabus on Z-score. I also have written some article on paper. So if you want, you can look back the paper which is written in 2012. I don't know whether you have started A-level by that time. So 2012, but unfortunately it was in Veerakesari. But my professor, Professor R.O. Tatil, he has given so many articles in different newspapers, especially look at Daily News and Times. in 2012, right? So I don't know whether you can get into all this just as a reference, right? Today we are going to talk about, in the connection of this, sampling distribution of X1. So sampling distribution of X1. How do you call this? How do you call this? Is sample mean. Sampling distribution of sample mean. Another term. Sampling distribution of sample mean. What do you mean by sampling distribution of sample mean? Look at this very carefully. Suppose, let's say, if a particular random variable is distributed normally with the mean of mu and with the variance of sigma square, with the mean of mu and the variance of sigma square. Now let's take the same population. So this actually, the population is this. This is the population. This is the population, right? That has been defined as this population. The random variable, take a particular variable. That random variable is distributed normally with the mean and the variance sigma square. Right? Now this is the population. Let's say, as we said, height, measuring the height, average height of students studying in University of Jaffna, as an example. So this is the overall population. All the students studying at University of Jaffna has been put into one population. So that is the population. Right. Now I'm going to take some set of sample from this population. So first sample, let's say N1. First set of sample, maybe 10 or 15, doesn't matter. Let's say 50 sample, which I say it as N1. So from that sample, I can calculate the mean. I can calculate the mean. So N1 and X1 bar. That is one set of sample. Take another set of sample where I put it as N2 and X2 bar. So likewise, I can get n number of sample where I can say the mean of that is Xn bar. Is it clear? So I am taking n number of sample, right? N1, N2, N2. Then I am taking the mean of that. So I am taking so many samples as such. Now, if I plot that sample, statistically, right? These are the values that I am going to plot it now. Statistically, we can say it is also normally distributed. Statistically, we can say it is also normally distributed with the same mean as the parent population. So the same mean as, if I draw the distribution, it will produce the same normal distribution with the same mean as mu, right? And the variance, right? I'll write it as variance sigma square by n. So the difference is only the variance. So if you draw the distribution for the sample mean, okay? So this is the distribution for sample mean. We are measuring the distribution for the, drawing the distribution for the sample mean. If you draw the sample mean, that will be also distributed normally with the same mu and variance sigma square by n. So we can write that the parent distribution is as such, so that the distribution of sample mean is distributed again normal with the same mean as earlier, the variance sigma square by sigma square by. Right. So this is the parent population. Parent population distributed with the normal mean mu and the variance sigma square, whereas the x bar, the sample mean distributed normally with the mean of mu and the variance of sigma square by n. Right. So here we can talk a little long. We can talk a little on the theorem. I will bring the theorem now. The theorem, it is called as central limit theorem. Central limit theorem. So what does this central limit theorem says? Right? Central limit theorem. So let's identify what this central limit theorem says. First, write down the first one. The x bar is normal when sampling from a normal population. X bar is normal when sampling from a normal population. All right. So this is what we said here. So that means the parent population was again normal. Normal means normal it is distributed normally. Parent population is distributed normally. The X bar distribution, if the parent distribution is normally distributed, definitely the distribution of X bar is also normally distributed. So that is the assumption. Right? That is the assumption. But in general, this is in general. I didn't talk about the central limit theorem yet. Right? So I'm going to talk about the central limit theorem. What does this central limit theorem say? So normally we have already found out from this that if the parent population is normally distributed, X bar is normally distributed. Right? So if the parent distribution is normally distributed, X bar is also normally distributed. This is from the earlier case. Now we are going to talk about what is this central limit theorem. Right now, in random sampling from a normal population, right? So that means I'm going to explain this. in a random sample, random sampling, in a random sampling from a normal population, in a random sampling from a normal population with mean mu and standard deviation sigma with mean mu and standard deviation sigma. The sample mean x bar has the normal distribution with mean mu and standard deviation sigma divided by square root of n as n sample size increases. As n sample size increases. Write down this theory part. So what basically says if x is distributed normally with the mean of mu and the standard deviation sigma, the x bar also will be normally distributed with the same mean as the mother distribution, but the standard deviation is sigma divided by n. So look at here, if the variance is sigma square by n, what is the standard deviation? If the variance is sigma square by n, so standard deviation means square root of sigma square by n. So this is equal sigma by n, right? So this is called as standard deviation. This is standard deviation. So this is what I have written here. Standard deviation, not the variance. So if you want variance, take the square of that. Right? Write down this. I will give, this is the starting point or the initiating point for the central limit theorem. So this is the initiating point for the central limit theorem. Basically what we said, if the mother distribution is normally distributed, the daughter distribution also will be normally distributed with the same mean, but the variance will be sigma square divided by n. So in other terms, standard deviation will be reduced, sigma by square root of n. Mean will be same, but standard deviation will be reduced. Can you all read these letters? you all read these letters? Can you all read these letters? Why? What is the problem? Tanupriya, what is your problem? Why can't you read this? Is it because of the color or is it because of the size of the letter? Why can't?
The size of the letter.
Are you watching by mobile?
Yes, sir.
Yeah, that is the problem. If you are watching, I am using a camera which is cost about 25,000 camera. So I think this is much visible. I don't know about others. Others, any problem? Because if you are watching, definitely by what do you call mobile, these letters will be very small. Definitely. Anyone? Anyone who are using laptops?
Yes, sir.
Can you all? How about the letter size? Maybe next time I will write it lightly. Write down. Tanuja, can you write down? Oh, whoever couldn't write down this, write down. In a random sampling, from a normal population with mean mu and standard deviation sigma, the sample mean x bar has the normal distribution with mean mu and standard deviation sigma divided by square root of n as n sample size increases. So n is the sample size. So in other terms, when we increase the sample size, this will come to true. That means the x bar also will behave like a normal distribution as the mother distribution, and with the same mean mu and with the standard deviation sigma divided by square root of n. Tanupriya, is it okay? Right. Hope I used to dictate what I write on the board, so at least people who cannot see the board clearly can write down your own notes. So that is my expectation. That is why parallelly I am writing and spelling out. So you better write the notes also. Okay. Right. Give me a second whether this pen colors. Right, we will use. Right, now we will come to this central limit theorem, definition of central limit theorem. Right, central limit theorem. So, definition of central limit theorem. Let's say this is CLT, central limit theorem. So, what is this definition? Definition of a central limit theorem. I will define and write it on the board. You can read it, then I will explain. Whatever the population the distribution of x bar approximately the distribution of x bar is approximately normal when n is large. Anupriya, can you see now? How about the letter size now? Anupriya, you're on. How about the letter size now?
Sometime only visible the slides, sir.
Anupriya, yes?
Sir, sometimes only visible the slides, sir. What is the problem? I don't know, sir, but sometimes only visible the slide
Yeah,
and voice.
I'm not using the slide. Huh? I'm using only the whiteboard today. I'm not using any slide. Huh? I'm
I
using
tell that, but whiteboard, sir.
not visible. So, where do you from?
Jaffna, sir.
Jaffna. How about other Jaffna students? Do you have? Is there raining there?
No, sir.
Okay. So this is visible, right? This. Anybody from Jaffna having the same problem as Tanuja? Yeah. So I get some information from other people also from Jaffna. I think they say it is okay. Maybe something wrong with Tanupriya's connection. Huh? But I try to write with the big letters, right? Okay, something wrong. Maybe yeah, yeah, yeah. I get some information from other students. It's not a problem. Maybe something wrong with your connection. Maybe you are in a very remote area, or could be where the signal is not clear enough. Right. Okay. We will continue. So, central limit theorem. What is central limit theorem? We will try to, because this is very important in statistics when you do sampling and so forth. Central limit theorem says whatever the population, the distribution of x bar is approximately normal when n is large. So what does it mean? What does it mean? When you say whatever the population, what do you mean by whatever the population? When you say whatever the population, that means the parent population could be normal or not normal, doesn't matter. So whatever the population means, the parent distribution may be normal or not normal. Can you remember this is a normal distribution? Can you remember not normal distribution? How do you call this not normal distribution? This is one example. There is another example. This is not normal distribution. What is that? We learn. What distribution? This is a normal distribution, symmetric and so on. We learn about it. What are these two? Not normal distribution. How do you call this? They have special names. Yeah?
skewed distributions.
Yeah, skewed distribution. Yeah, skewed distribution. Left skewed and right skewed. Fine, good. So here we said whatever the population. That means if the parent population may be normal distribution, maybe not normal distribution. If it is normal if the parent is normal distribution, don't worry because the daughter distribution also will be normal distribution. If the parent distribution is normally distributed, then the daughter distribution also normal. But what central limit theorem says, it doesn't matter. The parent distribution can be normal or not normal. Doesn't matter. However, if the parent distribution is normal or not normal, however, if you increase the sample size, the daughter distribution will be also become as a normal. So that is the central limit theorem says. That means if you increase the sample size, definitely that sample become as a normal distribution. So that sample try to behave like a normal distribution. Because why we are worried about this normal distribution is most of the statistical analysis are based on this normal distribution concept. If the sample is not normally distributed, then we cannot do most of the statistical procedures or statistical analysis. So one of the assumption is the sample has to be normally distributed. So if the parent population is not normally distributed, there are cases where the parent population will not normally distributed. And also sometimes in cases of sample, there are cases of samples also not normally distributed. That we are not going to cover in this particular course, right? Then what is the problem? If the parent populations are not normally distributed, sometimes if the sample size is small, then the daughter distribution also not normally distributed. So that is the problem, right? So because of that, the central limit theorem, what it says is that the parent distribution can be normal or not normal, doesn't matter. But the daughter distribution to be a normal distribution, we'll have to have large number of samples. So that is the concept. So it has to have large number of samples, right? Keep in mind. So the daughter distribution or the distribution which is coming from the parent distribution has to be, if it has to be normal distribution, then the sample size has to be large enough. So that is the concept, right? Okay. So sometimes if you type some of the keywords in your, you have internet facilities, keyword, central limit theorem, type, you will get a lot of definition, you will understand a lot of examples, right? That is the way that you can learn. Right. Now, let's say X bar is normally distributed. Sample mean, right? Sample mean is normally distributed with a mean of, let's say, 5 and the sigma square, let's say 25, and the sample size is n is equal to, right? How we can convert this into Z? So that is what we are going to look at it. So this is the statement: X bar is normally distributed with the mean of 5, with the standard deviation, sigma square 25, and the sample size is 9. So if you want to convert that kind of situation into Z, is given as x bar minus mu divided by sigma divided by square root of. So this is the Z conversion. If you want to convert a sample mean, this is how we do the conversion. So this is the Z conversion. So make a note of it. So this is how we can write down Z conversion. So according to that, suppose let's say I am asking a probability x bar greater than 2. I am asking a probability x bar greater than 4. I have uploaded some of the tutorial. Have you all got it in your LMS? Kamsatvani. Oh, Jeffrey. Are you all around? I don't hear. If you don't hear or if you have some signal problem, you can write on the chat. Huh? I have uploaded some of the tutorial. Have you seen anyone? Have you seen last week? No reply yet. Yeah, at least one reply is there. So I have uploaded some of the tutorial, right, relating to this kind of questions. So we'll have to practice that, right? We'll have to practice, right? Right. Can you find out what is the probability of x bar greater than 4? Find out the probability of x bar greater than 4. What is the answer? It is simple conversion. So here, this is same as probability of Z. We will put up first the simple one, and we will do less than 6. We will look at it less than 6 first. Right? Probability of x bar less than 6. We will see first easy one. So that is, if you convert that, this will become Z less than 6 minus, what is your mu? It is 5 divided by, what is sigma? Sigma is 5 divided by square root of n. What is square root of n? 3. Square root of n. Apply to this formula. So get me the answer, probability of Z less than some value. Somebody, can you work it out and tell me what is the probability value? Tell me the probability value.
0.7257.
Right. You all agree with that value? Just solve for this, right? 0.
Known as a whole answer. For that,
Yeah,
0.600.
6.
00.
Right. First, I need this answer. Then look at for this Z value of this. So this is indicating this is 0. This is the Z distribution. This is 0. So I want to find out the value, which is, let's say, 0.6. So this area, I want to find out that area. Right? What is the answer?
0.7257.
57. Right? Right. Can you try these 3? Find out these three. 1, 2, 3. So here, no difference compared to the earlier way of finding out the values. Only the difference is here. This derived diffusion component is different. So this is called as standard write down this may be very important, this word. Standard error of estimate. Standard error of estimate. That term is called as standard error of estimate. Can you try these three? What is the answer for the first three questions on the right side of board?
First one 0.3821.
Once again, 0. See, answer.
0.3821.
Right. Anyone got the answer for that one?
Sir, I think first one we have to
One minus.
1 minus, we have to subtract 1 minus.
Okay, so look at the convert first this into z. You have to convert this into z first. So after the conversion, look at the probability value. That probability value gives the left side probability. Now we'll have to get the right side probability. So this may be 1 minus this. Is that correct?
Okay, sir.
That is fine. What about the second one then? First you convert into z, then look at the probabilities. Because we have done this. Any questions? Second one? Anyone got the answer for the second one?
Zero point 2743. Bar, then 0.7257.
One. 0 point.
2743.
Yeah.
Mm.
That's right.
That's for 4. Then X bar.
That is for 4. Yeah.
2 answers, no, sir?
I didn't get it your answer. I will erase this. So that is probability of x bar less than 6 greater than 4. So that is equal. We'll have to convert this. So after conversion, what is the z values? Tell me the z values. What is the z values? 6 minus.
Minus 0.6
Huh?
plus minus 0.6 and plus 0.6.
But I have a bit of problem. Some
Minus 0.6
yeah.
and plus 0.6.
Right. Okay. So now tell me the probabilities, because we can say probability of z less than 0.6 minus probability of z less than minus 0.6. So we can write like this. Is it? So what is the answer for this?
$0.7257.
No, sir. The second P Z value is the 0.725, sir.
Yeah.
Minus 0.6, sir. The value is 0.2743.
Right? Is that correct? Correct?
Yes, sir.
Right. What is the answer? Final answer.
$0.4514.
0.4514. Okay. What about this? Try to do the third one. A less than x bar less than b is equal to 0.9. So that is basically is A, this is B. So this area is 0.9. So you asked to find out A and B. Can you tell me what is the value of A and B if you have done already?
0.05, sir.
No, I'm asking the value of A and B. So you have done similarly, right? Similar ones. So first you'll have to find out in the Z distribution. This is same as Z distribution, right? This is Z distribution. So here this is 0.9 again. So here Z1, let's say Z2. So what is this area? This 0.05. This area is 0.05. Now
Minus 1.65, sir.
minus 1.65, which is equal to the conversion of A minus 5 divided by 6 divided by 30. Solve this. And similarly, plus 1.65 is equal B minus 5 divided by 6 by 30. The same we have done last week, right? So only here is only x bar. If it is x bar, only additional information coming is root of n. Root of n. So solve these values, then you will get the A and B. Right? We take 5 minutes break. Not more than 5 minutes. I'm going to start a new topic. Right? Take 5 minutes break. I will start a new topic. Okay. I want to talk about few distributions that I will speak at the later stages. One is called as T distribution. The other one is called as chi-square distribution. T distribution, chi-square. Yeah, we will talk about these distributions first. Otherwise, it's complicated. So we will start with T distribution. It's called as T distribution or student T distribution. Sometimes it is called as student T distribution or T distribution. When you talk about this T distribution, right? If you look at some of the characters of T distribution, what are the characters of normal distribution? What are the characters of normal distribution? What are the characters of standard normal distribution? Standard normal and normal distributions are almost same, except in one concept. The mean is 0 for standard normal distribution. For normal distribution, any value can be mean, depending on what variable are we talking about. Population mean, right? So the rest is same, bell shape, symmetric, right? Right, here also T distribution, the mean value is 0. It is also a man-made distribution, so that mean value is 0. So in the T distribution, the mean value is 0. Right, T value is 0. But it is a symmetric distribution. It is mean is 0. Symmetric. Mean is 0. It is symmetric, right? The other characters, as the normal distribution doesn't say. What are the other characters? Bell shape. We said bell shape. So here it is not bell shape. So the T distribution is look like this. So assume that there is no bell shape. So the mean value is 0. Right? Mean value is 0. Right. Where we are using this distribution? The T distribution are used when the sample size is small. So we cannot assume the normality. Can you remember we talked about already a normality? When the sample size n is high, then we can assume normality, then we can go for Z test and so on. Right? Now here, when the sample size is small, we cannot assume the normality. Okay, when the sample size is small, we cannot assume the normality. The special character of normality is bell shape. So we cannot say this is a bell shape. It is symmetric. Mean is 0 in the T distribution, but we cannot apply the normality concept here. So that if the sample size is small, right? If the sample size is small, then we go for Z distribution. Sorry, T distribution, right? Right. What are the other special characters of T distribution? Let's look at some of the characters of T distribution. Mean is 0. Tail regions are more random. tail regions are more random. So this tail regions are more random. I have spoken to you in the previous lectures also. What do you mean by tail is more random? In a box plot, I discussed about that. Tail is more random. So tail is more random means, so this we have left side and the right side. It can take any value. So that means the tail region is very large. That is meant by the tail regions are more random, means tail is longer compared to the normal distribution. In normal distribution, tail is very short. Here the tail is long, right? Tail is long. So indirectly, what we say, it takes more random value. So if you take more random value, means tail is long. Right. One more character, the range of the value, like in standard normal distribution, the range is from minus infinity to plus infinity. The range is from minus infinity to plus infinity. Okay, so these are the characters of T distribution. If you look at the T distribution, so draw it properly. So draw it symmetrically. Yeah, this is a Z distribution. So this is a T distribution. Z distribution is right. Z distribution is something like this. Z distribution and T distribution. So here in T, when you increase the sample size, when you increase the sample size, right, T distribution will become as Z distribution. When you increase the sample size, T distribution will become as Z distribution. Okay? So T distribution is as such, the black color one. The Z distribution is Z distribution is the red color one. And also, if you look at the T distribution in terms right, so that is one way to express of the relationship between T and the Z distribution. Look at this one, because we said that the sample size, if the sample size is low, then we'll have to use T distribution. So this is your T distribution. If what is this DF? First or second lecture. What is this DF? Anyone? What is DF? Anyone? degrees of freedom. How we can write degrees of freedom? In terms of n. In terms of n, how can we write the degrees of freedom? I explained what is degrees of freedom in the second or third class. What is degrees of freedom? Anyone? Degrees of freedom is the number of total observation minus 1. Number of total observation minus 1. N minus 1. Degrees of freedom is total minus 1. And you remember, I took an example saying 10 balls are in a box, taking one by one. The last ball will be dependent, so that the degrees of freedom is n minus 1. Did I explain to you degrees of freedom? Yeah?
Sir, can you please explain that, sir? I didn't
I did
understand.
it earlier at the second lecture or third lecture. Can you remember when I spoke to the variance? All right? Variance are summation x square minus summation x whole thing square divided by n, then n minus 1. Don't you remember this formula? This is the first or second lecture. Look at the notes. So this is called degrees of freedom. I explained saying 10 balls inside, take one by one, right? 10 different color balls are there. So what is the chance of getting one ball is 1 over 10 at the first attempt. Second attempt, after taking one ball, how many balls remaining? 9 balls remaining. So what is the chance of getting one of the color ball remaining in the box? 1 over 9 and so on. At last, you have only 2 balls. What is the chance of getting one of these balls? 2 different color balls. So again, the probability of getting one of this ball is half. At last, there will be only 1 ball remaining in the box. What is the chance of getting that ball? 100% chance. So that is called as dependent. That observation is dependent. This observation is dependent. So the last observation is always dependent. So that we want to get the independent number of observation from a pool of observation that we have taken. So the degrees of freedom is always n minus 1. Total number of observation minus 1. The last observation we assume to be dependent observation. I did it long.
Okay, sir.
Maybe you all forget, right? So that is called degrees of freedom. So in the degrees of freedom, if you have low degrees of freedom, I mean, when the sample size is low, when n is low, definitely degrees of freedom is also low. So degrees of freedom is depend on the sample size. If the sample size is low, degrees of freedom is low. For example, if n is equal 5, what is df? Degrees of freedom? 4.
Okay.
If n is 20, what is the degrees of freedom?
90.
90. You see, when the sample increases, degrees of freedom also increases. Right, look at in a T distribution. I'll use another color pen. So here, this is high degrees of freedom, the red color one. The black color one is the low degrees of freedom. I have drawn only 2 diagrams. If the degrees of freedom increases, this curve becomes more and more towards normal distribution. So that is the principle. So the t distribution is more or less flat, lower distribution. Once the degrees of freedom increases, it becomes as bell-shaped distribution or bell-shaped diagram, right? So that is the principle behind the t distribution. So we said if the sample size are low, then we'll have to use the t distribution. When the sample size increases, then we can use the z distribution. That means when sample size increases, right? When sample size increases, t distribution approaches to the z distribution. So t try to approach z distribution when the sample size increases, right? So suppose as a thumb rule, if the sample size is less than 30, then we'll have to use the t distribution. Suppose if the sample size is more than 30, we can use the z distribution. If the sample size is more than 30, we can use, we assume that if the sample size is more than 30, that particular attribute is normally distributed, so that we can assume that since it is normally distributed, we can use the standard normal distribution table. Standard normal distribution table, right? Any questions? So I'm going to show you how to look at the table. Don't ask again how to look at the table again, right? Take the table. The table says student. Can you see this table? Anyone can't see the table? It says student t distribution table. So that is the table. How to look at the table? How to read the values of the table? How to read the values of the table, right? So the column wise we have t, or the probability. The row wise we have degrees of freedom, df. Degrees of freedom, df, right? Suppose if my n is, let's say, 10, right? So here we have values starting from degrees of freedom 1, 2, 3, and goes up to 100 in your table. So look at the value for 9. My degrees of freedom is 9. Right? Degrees of freedom is 9. So look at the value along the row of 9. Now we have the probability. Probability means chance of occurrence. So this probability, next week we will talk about the probability. We have a probability of alpha. So we'll have to decide what is this alpha. So based on this alpha, we look at what is the probability, p value. Suppose if my alpha value is 0.05, if my alpha is 0.05, so you have the probability, p value. You look at the p value directly, right? You look at the p value directly, 0.05. So that value will be your t value. So what is that value? Anyone?
2.262.
2.262. Right. What is this actually value? Suppose this is the t distribution. Mean, as we said, it is 0. Right? If you say the alpha value as 0.05, I will come to that. This by next week we will talk about. This is called as two-tailed situation. In two-tailed situation, if your alpha value is 0.05, here this is alpha by 2. This is also alpha by 2, right? It will give this area as the probability area. So this 2.26 is, it is positive because it is beyond 0, and negative in this other left side because it is symmetric. So this is how the table reads. So this alpha, you see, 0.05. So that means, what is this region? This area, it is symmetric. By area wise, alpha by 2. What is alpha by 2 here? 0.025. Here it is again 0.025. Okay. We will talk about this once we do the calculations. So this is called as two-tailed probability. So the alpha is given. So based on the alpha, what is alpha, that we will learn next week. Right, based on the alpha, keep in mind this table is read using the alpha value as the probability value and the degrees of freedom. Right? Okay. We will use this next week mostly. So that is about the t distribution or student t distribution. Another distribution that we want to learn is called as chi-square distribution. Chi-square. This is how we write the chi-square distribution. Right? Chi-square. Somebody has said cannot visible. Which one is not visible? Somebody has written not visible. You have to specifically say whether I am not visible or board is not visible. Because there are several objects. Yeah?
Board is not visible, sir.
Why? Now?
Only your voice is here, not visible board.
What is wrong then? What about earlier then? Earlier?
Earlier also like that.
Like that. Maybe something. You also from Jaffna? Maybe.
No, sir, no earlier.
No earlier. I'm not sure what is the problem. Okay, nevertheless, maybe some signal problem. Here we have good signal, I think. I'm at the university, so that signal is very good. But I'm not sure the UA area signal. Maybe anyhow, this is a peak time, no? So that is why. Right. Okay. So try to bear with that. Maybe once you get the video, you can listen very carefully. Right? And you can repeat and look at it again and again and get to understand. Right, chi-square test. chi-square distribution. What is chi-square distribution? Chi-square distribution, if you look at chi-square distribution, can you all see now again? I have drawn 3 color distribution. One is black color, then red color, then blue color. All right. So as an example, chi-square distribution, look at this black color. It is just a graph, not giving a distribution as such. What about second one? Red one. It is giving a distribution, it is a skewed distribution. Red one is a skewed distribution, right skew. Then the blue color, it becomes as like a symmetric distribution. So this distribution based on the degrees of freedom, low degrees of freedom, let's say 2 degrees of freedom, right, as an example. Then this is 5 degrees of freedom. Then this is 25 degrees of freedom. You see, when you have low degrees of freedom, it is not normal. When the degrees of freedom increases, this distribution becomes normal. Can you remember we talked about central limit theorem? In the central limit theorem also, it says initially the distribution may be not normal, but when you increase the sample size, it tend to become as a normal distribution. So this is an example, right? Initially the degrees of freedom is low, it is no more called as normal distribution. Then once you increase the degrees of freedom, it try to behave like a normal distribution, right? Chi-square distribution, again we will be using this distribution in this particular course, right? This is another example for a continuous distribution. Can you remember we put up different discrete distribution and continuous, the distribution for the variables on continuous. So T distribution, Z distribution, normal distribution, chi-square distribution are called as continuous distribution, right? Okay. So here it is a skewed distribution to right. Skewed to right, right? The range, actually range starting from 0 and goes up to plus infinity, always positive values. Range from 0 to plus infinity, right? The range is 0 to plus infinity. One more point. Here in chi-square distribution, it gives, look at here, this is for degrees of freedom 2, this is degrees of freedom 5, this is degrees of freedom 25. So we can say single distribution for each degrees of freedom. Single distribution for each degrees of freedom. Right? Single degrees of freedom for, sorry, single distribution for each degrees of freedom. single distribution for each degrees of freedom. So here also, take the table, maybe the fourth table. It says chi-square table. Can you all see? It says chi-square table, right? Chi-square table. Look at the value for the table. Again, the same way that we have already seen the table for what do you call the T distribution. Same concept. Suppose, let's say, if I want to look at the value for degrees of freedom 9 and the p-value 0.05, can somebody look at what is the value for 0.05 and degrees of freedom 9?
16.9.
16.9.
Yes, 16.9. Yeah, 9. Right? So this is how we can give the values for different degrees of freedom and different probability value. So how to use these values, we will see that in the following classes, not today. So we should be able to read the table. We didn't do any testing to find out the values. So we should be able to read the table. Right. Any questions? Any questions? Next week we will be starting a new topic. We'll be starting a new topic. So I didn't start today. I thought of starting today, but we'll start it next week, right? So I will see once if I can upload one by one. I will see, right? To upload all the notes or all the videos, right? Maybe we will try with a couple of first 2-3 videos first, and then we'll follow it, right? Okay, any questions? If not, we will stop. Thank you then. We will meet next week at the same time. Huh? Same link, same time. So, same link. Huh? Okay, right, bye.